Okay. All right, we're going to go ahead and get this thing started. If you guys want, there's some chairs up closer. If you guys want to scooch up just a little bit, looks like we got a pretty good crowd here. I want to thank our telescope guys out in the parking lot for showing us sunspots and solar flares. I'm going to kick this thing off here. So my name is Levi Beverly. I'm a associate professor with tenure at University of Louisville. I do cancer research. I've been running Beer of the Scientist since 2014. I actually had a memory popped up just this week of the very first Beer of the Scientist that we ever did in 2014. We originally started out at Against the Grain. Had a good relationship with those guys. A few years ago, just pre-COVID, we moved out here to Holsapple Brewing to do these talks. It was a little bit more convenient for me and a little bit more flexible. So here we are. We've done about, I think, over 60 to 65 Beer of the Scientist talks. I've personally given maybe 5 of them. Otherwise, they're all going to be talks that are given by other experts in the field. We've had the range of talks from Neanderthals to tropical rainforest studies to the artificial heart to 3D printing to basically anything you can talk about. And I think this might be our 3rd talk on astronomy, so we're really excited about that. Like I mentioned, the Facebook page, Louisville Underground Science, we have a couple thousand people who follow the site. I just post mostly Beer of the Scientist related things. That's, like I said, we're the live stream on there, so you can go and check out the talks later. We do have, I'm excited to, it's been on and off, as everybody knows, COVID sucked, and we got away from Beer of the Scientist there for a little while. We tried to do some online only things, and it just wasn't the same feel for me, so I wasn't excited about doing it. But now, we're kind of back in full force. We had one November, I think, and now you can see we've got at least the next 4 months planned out. So June 8th, I thought I had it worked out. Still trying to figure it out. I had some orthopedic or physical therapists / athletic trainers that were supposed to come and talk about sports nutrition, injury prevention, mental health of athletes. It could still happen, but we'll see. July 13th, I've got somebody from the Counseling Center at U of L. They're going to come and talk about understanding and dealing with the long-term mental health effects of COVID-19 pandemic, especially as it pertains to young adults. August 10th, we have one of our favorite and probably, aside from myself, the most frequent talker at Beer of the Scientist, Lee Dugatkin. He's from the biology department at U of L. He's given at least 3 talks before, and he's fantastic. He always gives a great talk. He shows up in full costume many times, and he's also he's an author. He's written numerous books, and he usually shows up and talks about one of his more recent books. This is called Power in the Wild: The Subtle and Not So Subtle Ways Animals Strive to Control Over Others. Strive for control over others. Sorry. And he's going to be signing some books while he's here as well. And then September 7th, we have a relatively new faculty member at University of Louisville in the bioengineering department, a guy named Joseph Chen, somebody I've collaborated and talked with. He uses bioengineering techniques and a lot of microscopy to look at how cancer cells and other cells move and interact with their environment. So I think there's going to be a lot of really cool pictures and videos and things like that. Just one other thing that I do also here at Holsapple, another way I try to help out the community is myself and a buddy of mine named Alan. We run a trivia night. I just wanted to throw this out here. June 14th is the next trivia night. It's $20 for a team of 6. This month we rotate the charities. All the money that we raise from the registrations and 25 cents per pint that you buy here at Holsapple goes to a charity called Options for Individuals. And they help physically and mentally disabled people and help find work and help them in the workforce. So it's for a good cause. And we've been doing that. Alan and I have been doing that every other month for about 3 years now. Okay, so what we have here, Beer of the Scientist, it's going to be about a 30-minute presentation. And then after that will be questions and answers. Our distinguished speaker will answer any questions you have. Once we're done with kind of the formal Q&A, I'm sure he'd be more than happy to hang out and answer any other questions that you might have one-on-one. So let's go ahead and get our speaker up here. So today's seminar speaker is Dr. Jim Lauroesch. He is in the Department of Astronomy and Astrophysics at the University of Louisville, which is
astronomy.
Just astronomy. Sorry, his PhD was in the astronomy and astrophysics from the University of Chicago. He's been at the University of Louisville for about 17 years. Prior to that, he was at Northwestern University. Spent some time in Maryland before that, if I remember correctly. And we're really excited. I had a lot of people reach out to me about their interest in this particular topic. He's going to tell us today about a brief history of telescopes and a little update on some new imaging technologies and some of the newest, the new hotness in astronomy and the telescopes that people are using right now. So without further ado, let's welcome Dr. Jim Lauroesch up to the microphone.
Got to get my top.
Oh, sorry.
Here. All right. So I'm just going to give a very brief review of the history of telescopes. I'm going to hit some of the high points, and then I'm going to go into the James Webb Space Telescope, which is the latest and greatest telescope. So the history of telescopes has always been new discoveries being made with each new large telescope. The first large telescope was Galileo, who made his 2-inch telescope, which 2-inch doesn't sound very big, but when it's compared to how big your eye is, it's a heck of a difference. So in 1609, Galileo, who did not invent the telescope, okay, the telescope was invented by, we're not sure. So, but someone in the Netherlands. Galileo made his telescope and was the first person, and really for a long time, the only person who turned the telescope up to the heavens. The main things he's known for are the moons of Jupiter, the 4 Galilean satellites, the 4 big moons of Jupiter. And he also was the first person to notice that the Milky Way wasn't just a band of light, but was actually countless stars. Now, in about 1800, William Herschel came along, and he had 4 different telescopes. His favorite one was the 6-inch telescope. His biggest one was the 60-inch telescope, which he did use, but most of his observations were done with his little 6-inch telescope. He also had an 18-inch telescope and a 12-inch telescope. Now, Herschel is most famous for discovering Uranus, the first planet discovered that was not visible to the naked eye. Now, technically, Galileo had noticed Uranus. He had seen it next to Jupiter and had observed it, but he didn't recognize that it was a planet. So Herschel was the first person to see it and recognize it as a planet. He also sketched, and in these days you didn't have photographic plates or CCD cameras. You had your eyeball and a sketch pad. And he sketched M51, the Whirlpool galaxy. And this was the first picture of a galaxy ever drawn. And he cataloged over 2,000 faint nebulae, which, if you've ever seen NGC catalog, that's generally Herschel's work. Now, Herschel's telescope didn't track. It pointed in one direction and you looked through an eyepiece and that was all you had. Now, later people started using refractors because the image quality of the reflectors of the day was very poor. So people used refractors, which is telescopes with lenses. And the world's largest telescope in 1863 was the Dearborn telescope, which was an 18.5-inch telescope. And this was made by Alvin Clark, who is the greatest telescope maker of all time. He built the world's largest telescope 6 different times. And he discovered Sirius B, the first white dwarf ever seen. In the early 1900s, the Hooker telescope, the 100-inch Hooker telescope, was built. And this allowed Edwin P. Hubble to discover the expansion of the universe. Just having the world's largest telescope allowed him to detect variable stars in other galaxies and take spectra of other galaxies, something that wasn't possible before then. Now, in the 1990s, the Keck telescopes were built. These use adaptive optics to observe the galactic center. And recently, Andrea Ghez, professor at UCLA, was awarded the Nobel Prize in Physics for discovering the 4 million solar mass black hole in the center of our galaxy. A telescope that I actually did some work on is the Sloan Digital Sky Survey Telescope. It's a 2.5-meter telescope, which doesn't sound very big. The Keck telescopes are 10 meters. The Sloan Digital Sky Survey Telescope is 2.5 meters. But it's designed to take surveys. It's designed to see wide angles of the sky. And it's mapped the cosmos in the Milky Way. In 1990, the Hubble Space Telescope was launched. Now, I've worked with the Hubble. I've had a number of programs on the Hubble. It's an incredible telescope to work with. One of the things that they did was the Hubble Deep Field, which was a stare at a blank piece of sky. So people said there's nothing in this direction. And Hubble just went and observed for many hours, something like 485 hours, at this one spot on the sky, and discovered over 3,000 galaxies. Now, Hubble, when it was originally launched, had bad optics. The optics of Hubble were ground to the wrong figure. This is because of basically they had washers in the wrong spot. And so the test stand was off. Now, the original wide field and planetary camera is on the left. It's a blurry image. In the first servicing mission, they launched up Wide Field Planetary Camera 2, which had improved optics to correct for the bad Hubble optics. And then in 2018, Wide Field Planetary Camera 3 was launched and had even better optics. So Hubble has been improved through the years. The Hubble Ultra Deep Field was the deepest probe of the universe taken at that time. And had countless galaxies in the image. Then, Christmas, a year and a half ago, the James Webb Space Telescope was launched. Now, even before Hubble was launched, people were sitting there coming up with ideas for a replacement or a follow-on to Hubble. The initial plan was a 4-meter telescope, 3 AU from the sun. This was a very ambitious proposal because only planetary probes had gone out that far. The idea to put it out that far was to get beyond the zodiacal dust. The dust that fills the inner part of the solar system and provides a background in the infrared. Now, this telescope was not launched. The telescope that became JWST, James Webb Space Telescope, began in 1994. Now, I was actually at Goddard Space Flight Center in 1995 to 1997. And there were meetings at Goddard Space Flight Center about JWST, then called NGST, Next Generation Space Telescope. And it was just, let's design the best telescope we can. And the original budget for JWST was $500 million. The final budget, including launch for JWST, is $10 billion. It ballooned. Now, JWST was originally supposed to be an 8-meter telescope. It was then shrunk down to 6.5 meter telescope to fit in the fairings of rockets. JWST actually had to be folded to fit in the fairing of the rocket. So the 3 mirrors on the side were folded in to enable the launch. And the telescope sits at the L2 Lagrange point, which is on the opposite side of the Earth from the sun. So it gets shadowed away from the Earth, the Moon, and the Sun. Its primary mirror consists of 18 hexagonal mirror segments. This is a way to build bigger mirrors. You don't build one big monolithic mirror. You divide it up into hexagonal segments and then glue them together, basically. The mirror is made of gold-plated beryllium. Beryllium is used because it's got low expansion due to heat. So when you chill down the primary mirror of JWST, you don't deform the mirror segments. They stay the same. Gold is used because gold is highly reflective in the infrared. And JWST is an infrared optimized telescope. Hubble uses silver coating because Hubble is optimized for the UV and the optical. Now, in order to make observations in the infrared spectrum, JWST must be kept under 50 Kelvin, which is minus 370 degrees Fahrenheit. Otherwise, infrared radiation from the mirror itself would overwhelm the observations. This is why JWST is such an advance over ground-based telescopes. Because ground-based telescopes are heated by the ambient air. And there's a background of photons just from the heat from the mirrors and from the air. So JWST also has this large sun shield, which had to be deployed, which blocks light and heat from the sun, earth, and moon. So JWST can point its sun shield at the earth, moon, and sun all the time at its position in the L2 Lagrange point, and then observe freely in the other direction. JWST has 4 instruments. NIRCam, which is a near-infrared imager, NIRSpec, which is a near-infrared spectrograph, MIRI, which is a mid-infrared imager and spectrograph, imaging spectrograph, and the FGS NIRIS, which is a fine guidance sound sensor and near-infrared imager and slitless spectrograph. Now, when they initially launched JWST, they had to align the mirrors. The mirrors were launched with them in resting position, and they had to be aligned correctly to make the final image. So each instrument had to be checked with the alignment of the mirrors. And so this is just the image sharpness check. Now, JWST is the largest infrared telescope ever launched into space. There were a number of previous imagers. There was IRAS, which was a low resolution imager. There was WISE, which was the Wide Field Infrared Survey Explorer, which was a relatively small telescope. And you can see the WISE image here. The points are very broad. Then there was the Spitzer Space Telescope. As an undergraduate, I actually worked on Spitzer. It was launched after I had already gotten a tenure track position. Took a long time. Spitzer was a modest size infrared telescope. And then you have JWST, which is a 6.5 meter telescope. And the images are very sharp. This is an image of Uranus with NIRCam on JWST. This is the best image we've had since the Voyager 2 satellite went by Uranus about 4 decades ago. You can see Uranus's rings. This is Neptune, and you can see storms on Neptune. You can see rings. This is the best image we're going to get for a long, long time. This is the Carina Nebula. This is about 3,700 parsecs away. It's a cloud of gas. And this was taken by NIRCam. This is the same field of view taken by MIRI, the mid-infrared imager and imaging spectrograph. You can see this looks quite different. MIRI in mid-infrared sees dust. NIRCam in the near infrared looks through dust. This is a NIRCam and a MIRI image of the southern planet ring nebula. And you can see that you pick up different elements in the two images. This is an HST image of the pillars of creation and a NIRCam image of the pillars of creation. And you can just see how many more stars you see in the near cam image. That's because the near cam image looks through the dust. And so you can see stars beyond the gas and dust that blocks the light in the Hubble image. This is near cam and MIRI of the pillars of creation. And you can see the near cam image highlights the gas. And you can see all the stars. And the MIRI image picks up the dust. Now, I have to say that both these images are in false color. These are not how you see it if you looked with your eyes. The near cam image is looking in the near infrared, so light just beyond what you can see with your eyes. And so what they do is they set blue for the shortest wavelength light, green for the middle wavelength light, and red for the longest wavelength light. And they make an image out of that so you can see what you would see if you had near infrared eyes. The MIRI image, the people at Space Telescope Science Institute use a color palette that emphasizes the dust and uses grays and blacks for the dust. Here's another comparison of the Hubble Space Telescope to JWST. This is an image of the same spot on a nebula. You can tell it's HST on the left because there's 4 spikes on the star. You can tell it's JWST on the right because there's 6 spikes on the star. That's due to the 6-sided mirrors. And you can see the HST image, which was taken in the near infrared, doesn't show the filaments that are seen in the JWST image. This is a protostar taken by JWST. Down in the center there's a disk of material, and inside the middle of that disk of material is a star that's just being born. And material flowing into the star is being ejected out in jets to either side. This is an image of the globular cluster M92 taken by NIRCam. This is 30 Doradus. This is a nebula in the Large Magellanic Cloud, which is a small galaxy that orbits our Milky Way. And the Large Magellanic Cloud has a lot of ongoing hot star formation. One of the regions is 30 Doradus. Now, when I was in graduate school, there was an argument whether 30 Doradus was a single star of about 1,000 solar masses, or a cluster of stars. And it wasn't until HST came along that we discovered that it was a cluster of stars. And now we can see it even better with JWST. Now, this was a discovery made serendipitously. People were observing a foreground galaxy cluster. And what they noticed in the background was a number of galaxies, about 9, in a distant cluster at a redshift of about 9. So this is a galaxy cluster that formed very shortly after the Big Bang. This was the ultra deep field taken by HST, and then Webb took an image of the ultra deep field. The Hubble ultra deep field took 11.3 days to take. The Webb image took 0.83 days. Just shows you what the advantage of having a bigger telescope is. So we have the 4 most distant galaxies observed by JWST. The most distant one of which formed 320 million years after the Big Bang. Now, these were discovered by taking deep images in multiple colors. And what you see is you see no galaxy, no galaxy, no galaxy, no galaxy, galaxy. And that tells you that the galaxy is at a high redshift, because the Lyman break is in your window. So these are spectra taken of those galaxies. Until you take a spectrum of a galaxy, you don't know for sure that it's really at high redshift. It could just be a red galaxy at low redshift. So you have to take the spectrum. And that's the advantage of JWST, is it has a spectrograph that is very sensitive and can take deep spectra of galaxies. All right. Well, that's what JWST is up to. And if you watch the news, you'll discover it's doing more and more and more and more and more. It's a really phenomenal instrument. Now, I should put in a call for HST, the Hubble Space Telescope. The Hubble Space Telescope is still a phenomenal instrument and does something that JWST doesn't do. Namely, takes pictures in the optical and the ultraviolet, and takes spectra in the optical and the ultraviolet, which JWST can't do. JWST only operates in the infrared. So if you want complete wavelength coverage, you need HST. All right.
Okay. I'll help with my questions. So we're going to take some questions now. I have one quick question, which is probably a stupid non-telescope guy. So if you're looking at these things that are light years away, parsecs away, what's the chance that there's not something between the telescope and what you're looking at? How does it?
There is the chance that you get something between the telescope and what you're looking at. Actually, we use that. That's a technique we use. I've used it a lot, which is you observe something in the background and you get a spectrum and you get the absorption due to the foreground object. And so you can tell what's in the foreground object by looking at the background object.
Okay. So I mean, I guess stupid question, but how do you see through that thing that's between you and what you're looking at?
It's you sometimes can, you sometimes can't.
Yeah, okay.
I mean, if it's one of these dense clouds like you saw in the mirroring images, you're not going to be able to look through it.
Gotcha. All right. Other questions? Yeah, Robert.
So on the James Webb, are all of those mirrors in the same plane, or are they incrementally
They're incrementally tilted.
tilted? Okay. And that's for focusing.
Yeah.
Oh, we got a
Technical definition. How far is the parsec? 206,267 AU. So 206,267 times the distance between the Earth and the Sun is 1 parsec.
why?
And you used L2 Lagrange point. What is that point actually?
It's a metastable point in the orbit around the Earth and the Sun. Okay, so the Earth orbits around the Sun. There are 2 points, one in front and one behind the Earth's orbit, that are called L4 and L5, that are stable. They're 60 degrees in front and 60 degrees behind. L2 is on the opposite side of the Earth from the Sun and is a metastable point. It's not, you put JWST there and it doesn't stay stationary. It actually orbits around. And it's just a point where the gravitational forces between the Earth and the Sun balance.
Yeah.
What about the light year? I thought that we measured things in light years.
Astronomers don't measure things in light years. We measure things in parsecs.
Gotcha. Is there an equivalency?
3.26 light years per parsec.
Oh, great. I had one
No?
The star that was being born that you showed is, I assume that light from that picture is millions of years old, so that star that was being born is no longer a baby star?
It's not millions of years. It's only at a few hundred light years. So it's only a couple hundred years old. So the star is still being born.
Oh, okay.
We're just seeing as it was a couple hundred years ago.
Oh, that's very cool.
Yeah. So that's the fun thing about astronomy is when you look out, everything you see is as it was in the past. So if you look at something like Andromeda Galaxy is 2.5 million light years away. So we're looking at it was 2.5 million years ago. So we see hot young stars in Andromeda that have already gone and blown up. We're just not going to see it for 2.5 million years.
So the baby star wasn't that far away?
No, that baby star is very close.
Oh, okay.
Over here, question? Yep.
What's the likelihood we'll observe a supernova in our lifetime, like,
In our galaxy?
or visible, like, or that we would know about? I know there
Okay.
was one in the 19th century. I'm just curious the likelihood we may have one.
There was supernova 1987A in the Large Magellanic Cloud. That was the closest supernova to us. The average rate of supernovae in a galaxy like the Milky Way is 1 per 100 years. We haven't seen one since Kepler saw one. So that's in the 1600s. So we're overdue for a big supernova.
I was gonna say, do we actually know he saw it? Like, he only had to draw it, right? There's no digital documentation that he saw it, right?
Yeah, he had to draw it. And he did it with his eyeball. He didn't have a telescope.
Yeah, I'm skeptical.
So when the telescope collects data, how long does it take from its current location to send that data here?
I actually don't
Here to
know
hold
the
something.
answer to that question. I don't know the answer to that
fair
question.
Oh, back
It
there,
will
yeah?
take, it'll take some time.
Yep.
So at first, I think you said that whenever there's like a new generation of telescopes, we always end up discovering something new, which is cool. But when we come up with a new generation of telescope, how do we decide what to look at first?
Okay, I'm gonna repeat just so people online. So basically, the question is, when we come up with a new generation of telescopes, it's going to be more advanced than the last generation. So how do we decide which thing to point at first? Yeah. Okay.
Basically, you just start looking. I mean, James Webb Space Telescope has made the discovery of the most distant galaxies, not by looking for the most distant galaxies, but by looking at something in the foreground, and just in the background there happens to be this ridiculously distant galaxy. You know?
Serendipity sometimes.
Serendipity
Yeah, I mean,
gets you.
yeah, again, yeah.
What is the James Webb going to do for our understanding of black holes? Like, I know we've gotten some very new black hole images like recently.
Well, the Event Horizon Telescope has done a lot for getting information about black holes. James Webb is taking images, or has taken images, of the black hole at the center of the galaxy, but they haven't been released yet. So I'm not sure what they're going to show. We'll see.
Let's see. Yeah.
What's one of the newest breakthroughs with the cosmic background radiation?
Oh, cosmic microwave background hasn't had a new satellite in a number of years. So we're kind of still stuck with what Planck, the last satellite that went up, told us about the cosmic microwave background. I don't know of another satellite that's been designed to go up and study the cosmic microwave background. I haven't heard of a new satellite. So I think we're kind of just stuck with what we have. There's some information coming from ground-based observatories.
I was reading the other today about the theory of the white hole. It could be the backside of the black hole.
White hole.
Right hole.
Know anything about a white hole?
Yeah.
Well, it was a theory that's the way it wrote up. What would be the object that we found black holes, but we haven't found the backside of it, where it's sucking in on the black hole side, shooting back to the galaxy away?
Questions about the backside of a black hole, which is a white hole.
Originally, when quasars were discovered, thought to be white holes. And then people studied them more and said, oh no, they're accretion disks around black holes. Nobody's ever seen a white hole. And it's just, it's a theory.
Maybe one last?
Yeah, I was just curious, before we were able to launch telescopes, how far could we actually see with telescopes here on Earth?
Okay, James Webb has been able to see further than any telescope here on Earth. But we've been able to see out about redshift 9, which is about 700 million years after the Big Bang. So about 13.1 million years ago. The thing is that the universe expands, and so something starts off 13.1 million light years away, and by the time we get the light, it's like 22 million light years away.
It's a moving target.
It's a moving target, yeah. The universe keeps expanding.
Okay, so just real quick before we end up, Dr. Lauroesch will hang around, I'm sure, and answer any other questions that you guys have. Please take care of Olivia in there in the tap room. We've been sitting here for a few minutes. Pay for your beers, close out your taps, give her an extra little tip. Come back for the next Beer of the Scientists and the trivia. We're always trying to do some fun stuff here. And last but not least, let's please give Dr. Lauroesch a big round of applause. Yeah, you did a great job. I appreciate it. Unplug that stuff. Those things will go up here.
David in here.